All right, so for this lab, first thing I want to point out, the lab begins by asking you to calculate the period of the piggy's motion as it flies around in the circle. Calculate the period of the piggy's motion by using just the length of the string, the radius of the circular path, theta, which you're going to figure out theta from L and R, right? That would just be, you would just go sine inverse opposite over hypotenuse like that. That's how you get theta. But what's the symbol for period? Who remembers the symbol we use for period? And period is the time for one complete circle. The symbol for period is capital T, right? Now, capital T. This poses a problem because one of the forces we have here is a rope. And what do we call force in a rope? Tension. So for this lab, what we don't want to do, we don't want to call the force in the rope tension and then have period be capital T, because then you're going to get confused. Which T is it, you know? So what we're going to do, we're going to call the force in the rope, we're going to call it force of string. Okay, so let's start out with a free body diagram. So here is the piggy flying around in a circle. The center of the circle is right here. Center of circular path is right here. Now, what forces are acting on the piggy as it flies around in a circle? There's only two. We have gravity, which is always straight down, and then we have the rope, which is at an angle like this. And we're going to call this force. Come on, Spaldo. We're going to call this force the force of string, so we don't confuse it with period. All right, now one thing about this lab, you'll notice the angle is off the vertical. Notice that the angle in this lab is off the vertical. Typically, we have angles off the horizontal, but it's no big deal. Just be aware, angles off the vertical. So we're going to put that on the free body diagram right here. So here is our theta, like that. Now, which force needs to be broken into x component, y component?
Force of string.
Force of string. Because if you look at the force of string, is it perfectly x? No. Is it perfectly y? No. So force of string has x component to the left, like this. That's going to be force of string x. And then we have force of string y, like this. Okay? The thing I want you to notice at this point, notice that force of string x points directly to the center of the circle, which means the force of string x component is the centripetal force. This force right here is the centripetal force because it's the only force that points to the center of the circle. Okay? And then speaking of the center of the circle, what do we always do to the center of the circle? We call the center of the circle positive. The reason we call the center of the circle positive is because the thing that always points to the center is the acceleration, and you want the acceleration to be plus because you sum the forces. The sum of the forces equals ma. Life is easier if that ma is always positive. Everybody got that? Okay, so center of the circle is plus. Now, after the free body diagram, we sum forces x, we sum forces y. Okay? How many forces are in the x direction? Only one. This force right here. Force of string x. So we're going to say sine theta force of string, right, using trig. So you want to put force of string x, you want to put it in terms of force of string. Any other forces in the x direction? Nope. So what's this going to be equal to? ma where this A is centripetal, because the centripetal acceleration always points to the center of the circle. Okay? And then, by the way, what can we plug in for centripetal acceleration?
V squared over R.
V squared over R. In fact, let's do that right now. Centripetal acceleration is V squared over R. So this is going to be M V squared over R. Yo.
How do you derive that?
Oh, where does V squared over R come from? It can be derived, but can I show you later? In fact, I'm not even sure I could pull it out of my brain right now. It's not an easy derivation. The question is, where does V squared over R come from? Let me show you later. Okay. Good question, though. All right. In the y direction, we have two forces. We have force of string y and mg. So this is going to be cosine theta force of string minus mg. Sum of the forces always equals ma. What's going to happen to this A right here? Is there any acceleration in the vertical? None. So this is just going to be 0. Okay, guys, we're almost there. What the lab wants you to do from this point is derive an equation for the period of the piggy flying around in a circle. If you look at what we've done so far, if you look at this, do you see period in there anywhere? Capital T? No. So how do we get period into this? Well, let me show you. There is a way. Yesterday I showed you one equation for the tangential velocity of an object. Yesterday we looked at this equation. Tangential velocity equals angular velocity times radius. And this is where I told you the story about the chain in the face. I was swinging it around, right? If you take angular velocity, and that has to be in radians per second. Angular velocity in radians per second multiplied by the radius, that'll give tangential velocity. Now, there's a second equation for tangential velocity. The second equation for tangential velocity is this. Now look, let me explain it first. If something's going around in a circle, so say I'm swinging this rubber stopper right here. Let's just look at this. I'm swinging this around in a circle. If we want the tangential velocity, which is a linear velocity, it's meters per second, one way to do it is you take the distance around the circle. So what's the distance when I swing the rubber stopper around? What's the distance around one circle? 2 pi r. So all we're doing is we're using the basic definition for velocity. Velocity is distance over time. So let's apply that to one circle. What's the distance around one circle? 2 pi r. What do we call the time for one circle? The period. So we take this equation here for velocity and we plug it in up there, which, what do you notice now? We're plugging into a kind of a not too friendly situation because this velocity is squared. But still, it's very doable. So when you plug that in, here's what you're going to get. So we plug in here, this is going to be equal to m 2 pi r over period squared divided by r, like that. That's 0. Now, what you're going to do is you're going to take these two equations here and combine them. When you combine these, what you're going to get is period equals 2 pi square root r over g tangent theta. Now, should you memorize this equation? No. This is a derived equation, but it's pretty cool. You can get this equation from these two equations. So let me just show you how you do it. How can you get this equation for the period from these two equations? What you're going to do is you're going to divide these two equations. So put a big line right here. You're going to divide the two equations. What's sine divided by cosine? There's your tangent right there. Okay? What happens to the force of the string? The force of string cancels. The mass will cancel. And then what you're going to do is you're going to solve for period. It just becomes algebra. And this is what part 3 of the lab wants you to do. So final thought here. Look, the lab has 2 different periods. You're going to see T sub C and you're going to see T sub M. T sub C is your calculated period. That's this. You're going to calculate the period. T sub M, you're going to bust out a stopwatch. The M stands for measured. You're going to measure the period by timing the piggy. If I were you, let the piggy go around 5 times or so. Time 5 complete circles. Get the time for that. Divide by 5. And then that's your measured period.